Hi, I'm Michael Pfeifer. This is another episode of the Metal Conversations podcast. A couple of weeks ago, I discussed two case studies. One involved a manufacturing quality problem where we discovered that there was a problem with the grain size in the metal, and it was a problem with both the steel making process and a problem that my client was not specifying the grain size in their specification for the steel. Things were put in place to address both the steel manufacturing problem and the grain size and the specification, and those things helped prevent the future orange peel from occurring in the bowls. In the other example, it was for a faucet failure, a faucet that leaked inside of a building that caused over $100,000 worth of damage. In that case, I was not involved with identifying corrective actions. I just determined why the thing failed and determined the root cause of the failure. Today, I'm going to talk about a project that involved parts breaking in a piece of equipment that was resulting in a lot of unplanned downtime. And I was involved in doing a failure analysis, the root cause analysis, helping identify the corrective action to prevent the problem from occurring, and then helping with implementation of the corrective actions. So the problem involved stainless steel paddles that were used in industrial mixing equipment. And these paddles were fracturing during use. The paddles consisted of a machined bar that was welded to a stainless steel plate that was about 6 inches wide and about a half an inch thick. The paddles were attached to a shaft that ran inside the length of the equipment, and the paddles were screwed into the shaft. And so the shaft and the equipment would spin around, and the paddles that were attached to the shaft would then spin through the equipment and were used to mix material that were inside of the equipment. As the shaft rotated, the paddles stirred the material being processed. So the problem was that the paddles were bending and were breaking. And it was, as I said, they were resulting in a lot of unplanned downtime. So I was given samples of a couple of fractured paddles, and as well as background information about the paddle specifications and how the paddles were being used and the circumstances of the failures. And then I did metallurgical analyses on the fractured paddles, and that include visual and stereo zoom microscope exam of the fracture surfaces, scanning electron microscopy of the fracture surface to try to identify the fracture mode, also metallography, composition analysis, and hardness testing of the blade stainless steel material, just to make sure that there was nothing wrong with the blade material. So it turns out that there was nothing wrong with the blade material. It met the requirements for 304 stainless steel, which is what was specified. The stereo zoom analysis and the SEM analysis revealed that the blades were fracturing due to fatigue, where fatigue cracks were forming and growing on both sides of the blade, and they'd form on the outside of the blade and work their way inwards. The fact that there was two fatigue cracks, one on both sides of the blade, indicated that the material was exposed to reverse bending. Now that seemed odd because the shaft only spun in one direction, and so the blades should have only been moving in one direction, and also the blades were not exposed to very high stresses when mixing the material. But somehow the blades were exposed to cyclic bending stresses. The other thing that's important to know is that the failures were occurring at the tip of the weld where the blades met the stem or the piece of metal that the blades were welded to. So the end of that weld was a stress concentration, and the cracking was occurring right at the end of the weld. Failure by reverse bending fatigue seemed odd because the equipment shaft only spun in one direction. I spoke to someone who works at a company that makes motors, and he's an engineer who works at that company, and he explained that the voltage supply to AC motors can have some variation. So the voltage can vary between a high and a low value. And the variation in the voltage will result in acceleration and deceleration of the motor shaft. And the larger the variation of the voltage, the larger the accelerations and deceleration can be. So I realized that this was the cause of the reverse bending, that there must have been a large voltage variation that was causing acceleration and deceleration of the motor shaft and the equipment, which was then resulting in the blades accelerating and decelerating so that the blades were exposed to bending stresses on both sides of the blade. So I spoke to my client and I told him about this, and he went and investigated it, and he found that the voltage supply and a cable that was providing power to the equipment, that there were problems with both of them, and that there were very large voltage variations, that there were voltages over 1,000 volts. And this was 440 volt equipment. So the voltages were much higher than they should have been. And one thing he determined was that the cable between the motor and the power supply was not good. And that cable was replaced. And also things were done to the power supply to clean up the voltage variation a little bit there. After he did that, the failures decreased. They didn't go away. And what they had to do is run the equipment at slightly lower speeds in order to reduce the voltage variation on the equipment to prevent the problem from occurring. The other thing that was done was, rather than making the blades out of two pieces by welding them together, they decided to have parts cast out of one piece so that there wouldn't be the stress concentration at the weld joint. When that was done, combined with the voltage, with the changes to the power supply and the cable, then all the problems went away. So this is an example where the information from the failure analysis was used to understand the root cause of the problem. And then with that information, it was then possible to identify corrective actions and put those corrective actions in place to prevent the problem from reoccurring. The fulfilling part of this project to me was in helping the engineer get the information he needed to help understand what was going on with his equipment and prevent the problem from recurring. Now, I've been working as a metallurgical engineer for over 30 years. While many interesting technical challenges come up, the most gratifying part of what I do is helping people apply this engineering discipline, metallurgy, which is often overlooked, and helping them apply the tools and the knowledge to get the answers they need to help solve problems and make decisions. I know that a lot of engineers are kind of mystified by metallurgy. Have to think small, microscopic, and the tools that metallurgists use to get information, people aren't really that familiar with them. And there's just not the same rules that apply to other disciplines that apply to metallurgy. In mechanics, we rely on Newton's laws of motion, and in electrical engineering, they rely on Maxwell's equations, and those simple equations lead to very complicated things, but everything boils down to those equations. In metallurgy, things aren't nearly as simple, and there's a lot of things to understand, and sometimes it can seem almost like alchemy. But to me, what's really cool is that by understanding the metals and understanding the metallurgy and applying the tools, that I can help get information needed to understand what the metal is exposed to, and then help understand the problem that was occurring, and then help figure out how to fix the problem. And the other part to me also that's gratifying is doing the whole part, not just doing the failure analysis, but then helping to apply the failure analysis information to understanding the root cause of the problem and identifying the corrective actions that needed to be taken to prevent the problem from recurring. And doing all those things is very gratifying, as well as working with the engineers that I work with, because without exception, these are all very smart people in their fields, and I learn a lot from them about what they're doing, and we apply that information together to understand the problem and fix it. One of the morals of the story is it's important to get the data. The cost of a failure analysis is small compared to the time wasted guessing at solutions that don't work, and the money that is lost due to continued product failures or equipment downtime. And without the information from a failure analysis, it's extremely difficult to identify the root cause of failures. In this particular case, with this example, we got the data in about 2 weeks, and we just had to wait for the data from the lab. And once we got the data, I just had to speak with the person I knew at the motor company. That was another day, and we were off on figuring out what the root cause of the problem. So that's it. If you have any questions or comments about this podcast, let me know. My email is mike@imetllc.com. And if you haven't already, subscribe to the Metal Conversations podcast series to receive alerts for when new podcasts are released. You can subscribe on Spotify, Google Podcasts, Apple Podcasts, and all the other outlets that offer podcasts. Thanks again for listening, and good luck with your metals. Bye.